We are now going to go in a more theoretical and less mathematical direction. So we've finished up our calculations for this chapter. Now we want to just look at some broad ideas. And the first idea I want to look at is oxidation and reduction. And we will look at this topic now in this chapter, and then we will revisit it again in later chapters when we talk about organic chemistry and biological chemistry. So many of the reactions that we carry out can be described as oxidation or reduction reactions, and we combine these terms and call them redox reactions for short. If we are to simplify the term oxidation to its most easy to understand level, what we will say is oxidation is a loss of electrons and reduction is a gain of electrons. So let's say we are looking at the reaction between sodium and chlorine. We know that sodium metal has a charge of 0, and we also know that as a metal, sodium would like to lose its valence electrons. So it only has one valence electron, and since it's losing an electron, we say that it is being oxidized. And on the other hand, chlorine is gaining electrons and becoming Cl-, so we see that chlorine is being reduced. So as we've just seen with this last example here, we can almost always simplify this process to just say that a metal is oxidized in the reaction between a metal and a nonmetal, and a nonmetal is reduced. We can take the reaction that we just saw and make it a little bit easier to see by separating it into what we're going to call half reactions. So one shows only the part of the metal and the other shows only the part of the nonmetal. So here is the original reaction that we were looking at. Here is just the oxidation part. So what I've done is I've taken out only the sodium. So we see here sodium metal with its 0 charge. It's becoming sodium ions because sodium chloride is an ionic compound. And in that process, remember, we can't destroy matter, and electrons are matter. So we can't just get rid of the electrons. So we write that they are given off as a product. It's losing them. They're being separated away. And so for an oxidation, the electrons would always be on the product side. As you would imagine, for a reduction, it will be the opposite. In this case, we see chlorine, and it is accepting 2 electrons. Those are the electrons that come from sodium, and now it is becoming chloride ions. So we call these here the half reactions. You'll see that they are balanced. It might seem odd that we have a 2, a 2, and a 2 here, but those 2's have to correspond to what we have in the original reaction. You are not required to be able to write half reactions in this class. I just wanted to clearly illustrate that sodium was in fact being oxidized, its charge was in fact increasing, and that chlorine over here, which has no charge, is being reduced because its charge is decreasing. And this is probably the easiest way to illustrate that. Let's look at another example. So we've already talked about here forming sodium chloride, and we saw that the sodium was being oxidized and the chlorine reduced. How about this case? The zinc is going from neutral to 2+ charge, so the metal is being oxidized. Oxygen is accepting electrons from zinc, so oxygen is being reduced. Its charge is decreasing. There are more complex applications of this kind of reaction, as I mentioned before, when we get to organic chemistry. But just to give you a preview of it, when it's not clear what's going on, whether there's an oxidation or a reduction reaction, we can usually say that if any chemical is gaining oxygen atoms, it is probably being oxidized. And if something is gaining hydrogen atoms, it is probably being reduced. We'll see that more later on. I now want to combine some of the concepts from the last chapter, chapter 4 on energy, with what we know of chemical reactions now. So when we have a chemical reaction, there's always the breaking or forming of chemical bonds, usually both. It is important to know that to break a bond, we always must invest energy. So energy is always used up when that occurs. On the other hand, whenever a new chemical bond is formed, energy is released. This also applies to intermolecular forces. So whenever we need to break intermolecular forces, we have to put energy in. We saw that with boiling water. In order to boil water, we have to add a lot of energy in to separate the hydrogen bonds between the water molecules. So we've already seen the term exothermic referred to an exothermic process. If we're specifically talking about chemical reactions, what we say is an exothermic reaction is one where more heat is given off than consumed. And so our combustion reactions, burning things, like for example burning a candle, is an example of an exothermic reaction. Burning gasoline is an exothermic reaction. We know this because if we go touch the hood of a car engine, it's going to almost always be warm right after it's been used. And so an endothermic reaction is one where more heat is consumed than given off. We have to put more energy into it than we get out. Now, the way that we show this on a chemical reaction is by providing a value for what's called the heat of reaction. And we symbolize that here with this delta sign and H. H is technically called the enthalpy, but it's easiest to understand this as heat. So we read this as change or difference in heat. Whenever this has a negative value, that means that the reaction is exothermic. Heat has been lost. And if delta H has a positive value, the reaction is endothermic. We can usually look up the values of delta H in various tables, and we're not going to practice looking that up in this course. But let's look at one example where I have looked that information up, and that is the reaction of carbon with oxygen to form carbon dioxide. And you'll see here that I have listed the value of the heat of reaction, and it is a negative number. That means that this reaction is exothermic. Negative value of delta H means we have an exothermic reaction. We're not going to worry about doing any of the math involved with heat changes here, but just so you know what this means in words, we could say that this says that every 1 mole of carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide and gives off 394 kilojoules of heat. And I don't say it gives off negative heat. That doesn't make sense. The negative just tells me that the heat is being given off. That's what the negative sign means. And if the sign had been positive, that would mean that heat was being consumed. That means we would have to be constantly supplying heat to get this process to go, so that to make 1 mole of CO2, we would have had to invest 394 kilojoules. Going in a different direction, now let's talk about the speeds of the reaction, also called the reaction rate. So the reactions that we've seen so far in the lab usually occur extremely rapidly, but that is absolutely not the case for all reactions. Some reactions could theoretically take years upon years to proceed, which would be definitely a problem. Other reactions maybe take an hour, 2 hours, maybe a day. So when we use the word rate in the context of reactions, what we're saying is the change in the concentration in a reactant or a product over some interval of time. If we say that a reaction is going to the right, then what that means is that the reactants are being used up, and so their concentration change is negative. We see them being used up, and the change in the concentration of the products is positive. Imagine, if you will, that you're cooking a cake. The reactants could be seen as being the flour, the eggs, the sugar. Their change is negative, while the change in the amount of cupcakes or cakes that you're making is positive. They are the products. Now, although the book doesn't really talk about this much, I want to introduce the very basics of what we would call collision theory. And this just is useful for understanding what's going on in a chemical reaction. So, according to collision theory, for reactions to occur, reactants have to collide with each other with sufficient kinetic energy. And recall that kinetic energy was the energy of motion. So they have to hit each other with, for example, the right amount of speed. And we call that the energy of activation. And also, they have to collide with each other in the correct orientation. So any old collision doesn't necessarily lead to a reaction. They are both required if we're going to form any new reactants, any new products, and if we want to break any bonds that are already in existence. So let's look at this in a graphical example. Let's say, for example, we are trying to react nitrogen and oxygen. And this blue molecule here represents nitrogen, and the red represents oxygen. And so we're kind of looking at this in like a slow motion. So the nitrogen and the oxygen are coming together, but let's say that they need to be parallel to each other. So if the two nitrogens here are drawn along this axis, let's say that the oxygens have to be facing the same way. If they're in the wrong orientation when they collide, there will be no reaction. And so the molecules just bounce off of one another. Since molecules are approaching each other from random directions, that means the vast majority of the time they are not going to collide in the right orientation. They have to hit just right. Also, if they come together too slowly, that is, they don't have enough kinetic energy, even if they're in the right orientation, which is what we're trying to show here, that won't be enough energy for the bond breaking to occur between the nitrogen and the oxygen with the oxygen, and therefore they will just bounce off of one another, and there will not be a reaction observed. Here's an example where a reaction might occur. Let's say we have a hydrogen gas and an iodine gas. They are approaching each other in the perfect orientation, and they are approaching each other with a lot of energy. And as they smash into one another, what happens is the bonds between iodine and iodine atoms break, and the bonds between hydrogen and hydrogen atoms break. So, again, they must hit each other in the right orientation and with a certain minimum amount of energy for there to be a reaction. And in most cases, collisions do not lead to reactions. So, if we want to speed up a reaction, what we need to do is we need to look to collision theory to see how that's going to happen. First of all, we need more collisions. The more collisions, the more likely molecules are to hit each other in the right orientation. Also, we need the molecules to have enough kinetic energy, or in this case, enough speed for those reactions to occur. And so there's a few ways that we can do this, but the two most common ways that we can increase the speed of a reaction are, number one, to increase the concentration of the reactants. The more reactants you have, the more likely they are to collide with one another, assuming that you're keeping them in the same volume of space. The other way, and let's think about this, we're trying to speed things up. We want to add kinetic energy. What was the measure of kinetic energy? It was the temperature. So we can raise the temperature. And if we do that, that will usually increase the rate of reaction. And it's an interesting general rule that we can mathematically show that if we raise the temperature by about 10 degrees Celsius, that essentially doubles many reactions rates. And there are other techniques. For example, we can increase the surface area by grinding chemicals into powders. The greater the surface area, the faster reactions tend to occur. But we're not going to worry about these other techniques right now. Energy diagrams are very useful ways of illustrating the changes of energy in the reactions as well as the speeds of the reactions. And so they're just going to be rather simple graphs here. And what we can find out from the energy diagram is we can look at one and say, do we have an exothermic reaction or do we have an endothermic reaction? And we can compare two different energy diagrams, and by looking at them we'll be able to determine which reaction is faster and which one is slower. So we represent this with a simple x and y type of an axis. The y-axis, the vertical axis, is energy, and the horizontal axis is something called the reaction coordinate. And if we want to be more simple about this, we'll just think of this as the progress of the reaction. It's not strictly supposed to stand for time, but imagine if you were watching a movie of the reaction. If you were going from left to right, that shows the changes in energy as the reaction proceeds. So we're always going to read it from left to right. And this is what a typical energy diagram might look like, what we call a one-step reaction. And we're only going to look at one-step reactions in this class. In other words, there will be only one hump. So the starting points and the ending points in this diagram stand for the energies of the reactants and the products. So if we look here, I've got this line kind of flat here. Since this is the energy axis on the y-axis, this is the energy of the reactants right here. And then the energy of the products would be down here. If this were, for example, 50 kilojoules and this were 10 kilojoules, then we would see the difference is it goes down from 50 to 10, a difference of 40 kilojoules. But for now, don't worry about labeling numbers on here. So for an exothermic reaction, the energy of reactants is greater than products. In other words, if we compare just these 2 points, that's all we have to compare, the beginning and the end. If the reactants is higher than the products, the reaction is going to be exothermic. If it were the other way around and the products were higher than the reactants, then that would represent an endothermic reaction. And so the difference in the heights of these positions is going to give us that value of heat of reaction, delta H, that I mentioned a moment ago. So I'm just going to take this point here and draw it out as a straight line, and that just stands for the energy of the reactants. If I go ahead and compare the energy of the reactants to the products, that is our delta H value. That's the heat of the reaction. Since the energy is going down, we say this is an exothermic reaction. We're always drawing the arrow here from its starting point to its ending point. Let's look at this reaction here. So I've taken the reactants and I've drawn the line out. And this must clearly have to be a different reaction because different reactants, different products, the energies are fixed depending on what the reactants and the products are. So different reaction. Reactants are lower than products. So the change in energy is positive. This is telling me that this reaction is endothermic. So again, it's a simple comparison. If the products are higher in energy than the reactants, it is endothermic. On the other hand, if the products are lower than the reactants, it is exothermic. The highest point in a diagram represents what we call the transition state. And the transition state is that point at which bond breaking and forming is at its maximum. This point will always be higher than the starting or ending points. It's always going to be the highest point in the diagram, somewhere in the middle. And so in other words, it can never go down. It must always go up from the reactants. So the difference in energy then between the reactants and the transition state is called the energy of activation. And I've got that labeled here. So we want to be sure not to confuse this with delta H. So remember, delta H is the difference between reactants and products. EA, energy of activation, is the difference between reactants and the transition state. And the value of the energy of activation is always positive. So the arrow will always be going up to the transition state. Now, how high this transition state is very useful. The higher the energy of the transition state, the slower the reaction. That means generally the fewer collisions that actually lead to reactions. So a very high value of this means the reaction is kind of slow. So just going back and looking at the example that I was talking about a moment ago, these are our reactants. This point here, where they are colliding and the bond breaking and forming is occurring, that is the high point on an energy diagram. This is the transition state right here. And these just represent the energies of the products. So here we have a couple different ways of illustrating a particular reaction here. You'll notice that the height of the energy of activation here is smaller than the height here. So which one of these is faster and which one of these represents a slower reaction? Remember, the higher the energy of activation, the slower the reaction. So the reaction on the left would expect it to be faster. The reaction on the right would be expected to be slower. If we wanted to speed up this reaction, we could, for example, heat it up. If we heat up the reaction, more reactants will be able to get over that energy hump. If we keep the temperature too low, the reactants won't have enough energy to get over the hump, and the reaction will be too slow to even observe. Another way that we can increase the speed of a reaction is by adding a type of chemical called a catalyst. By definition, a catalyst participates in the reaction, but it is not consumed by it. And so usually when we write a chemical reaction, we write it over the reaction arrow. It's not a reactant because it's not used up. And since it's not used up, it can typically be reused over and over and over until, for whatever reason, it might physically degrade and not be as useful. So what this does is to lower the value of EA. Technically, it actually offers a different path, but it's always a lower energy path. And remember, the smaller the value of energy of activation, the faster the reaction. So that's what a catalyst does. Now, finding the right catalyst for a reaction is not at all a trivial matter. It requires, in many cases, lots of research. So catalysts aren't just laying about on trees, so to speak. We have to do a lot of research to find a good catalyst for a particular reaction. And unfortunately, they tend to be very expensive. That's not always the case, but many catalysts include things like platinum in them, which are very expensive. So one example that we see in the lab in our respiratory gases experiment is where we're trying to break down hydrogen peroxide to make water and oxygen. When hydrogen peroxide decomposes normally, the process is incredibly slow, and it might take years. Obviously, that's not practical in a lab. It turns out that the chemical manganese 4 oxide catalyzes this reaction, and it occurs extremely rapidly when added to hydrogen peroxide. Now, just because manganese 4 oxide works for the hydrogen peroxide reaction, that tells us nothing about how it will affect some other random reaction. We only know that it works for this reaction. If we are looking for a catalyst for another reaction, it probably wouldn't hurt to try it out, but it doesn't mean it's going to do anything. Our cells contain enzymes, and particularly we have a rather high concentration of enzymes within our livers, and these enzymes are proteins, which are our catalysts for our biochemical reactions. A huge number of the reactions which occur within our bodies would be way too slow to keep us alive ordinarily, and so these enzymes are needed to speed up the reactions so that they occur. I can also decompose hydrogen peroxide, for example, with a piece of liver. Obviously, using human liver is not practical, but if we were to use cow liver and put that into hydrogen peroxide, it would be a rather smelly reaction, but it would definitely have the same effect as manganese 4 oxide. Now, incidentally, these are all huge topics, and in our Chemistry 140 class, we spent an entire semester going over what I've just talked about for the past 25 minutes, because there's a lot of details that we are leaving out. And this next topic is another one that normally would take weeks of study, but we're just going to look at it from a very high-level view. And this is the topic of equilibrium. So let's look at a reaction here. So we have nitrogen reacting with hydrogen to form ammonia, and I've indicated that they are all gases. Now, for what we know at this point, we think that 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. And unless you're told otherwise, that's going to be a reasonable assumption for this class. But it's actually a much more complicated situation than that. What will happen is when you add the nitrogen and the ammonia and the hydrogen together, they will form ammonia, and then the reaction will start to slow down, and then at one point it will appear to stop. You'll still have nitrogen, you'll still have hydrogen, and you will have made some ammonia. And it seems to have stopped. In reality, the reaction hasn't stopped. What's going on is you are forming ammonia at the same rate that the ammonia is breaking down and giving you back your reactants. What we are said to be at is a state of equilibrium. So at equilibrium, it is a point at which the concentrations of reactants and products is no longer changing. So it seems like the amounts of all the chemicals are constant. So going back to our concept of rates, what we say is the rate of the forward reaction, so the rate that nitrogen and hydrogen are reacting with each other to make ammonia, is essentially equal to the rate of the reverse reaction, the rate that ammonia is breaking down. Equilibrium is dynamic. As I said before, even though it looks like the reaction has stopped, what's actually going on here is that the reaction going from left to right is going on at the same rate as the reaction from right to left. So although we don't see changes, they are still occurring. Le Châtelier's principle gives us an idea as to what will happen when we have a system at equilibrium that we disturb. So let's say we have our reaction and it's at equilibrium, and then we cause some kind of a change. So, for example, we might raise or lower the temperature, we might raise or lower the pressure, or what we're going to look at, we might add or remove chemicals from a system which is at equilibrium. According to Le Châtelier's principle, if we have a system at equilibrium and we disturb it, we change it to take it out of equilibrium, the system will spontaneously change in a way to get back to equilibrium. Probably the best way to think about this right now is to imagine a teeter-totter. And let's say we have our teeter-totter and it's totally level, totally balanced. If you go and push down on the right side of the teeter-totter, you have disturbed the equilibrium. And as soon as you release your hand, what's going to happen? Well, that right side will go right back up and the left side will come down. Equilibrium is still disturbed, but now in the wrong way. So the teeter-totter will reverse its position, and it will keep doing this until it gets back to equilibrium. So in a way, it's like a pendulum. So the important thing to get out of Le Châtelier's principle is this. If we are using up reactants to form more products, we say that our reaction is shifting to the right. And if we're going the other way, if we are consuming more products and forming more reactants, we are saying that the reaction is shifting to the left. So let's look at a practical example. So let's say here that I have nitrogen, hydrogen, and ammonia gases, and they are all at equilibrium. And you will notice here that I'm using a different kind of reaction arrow. This kind of arrow calls out that this is a reversible reaction, meaning it can go from left to right and from right to left, and indicates that we can have an equilibrium here. So, let's say we're at equilibrium. Now we're going to disturb the equilibrium. So let's say we inject into our reaction mixture extra nitrogen. So then we're no longer at equilibrium. The amounts are no longer in the equilibrium amounts. What Le Châtelier's principle tells us is, now that we have excess nitrogen, it will react with any extra hydrogen to start forming more ammonia. So we say that the equilibrium shifts to the right. So that's an important thing to take into account. Adding more of a reactant to a system at equilibrium shifts the equilibrium to the right. You will start to form more ammonia until you reform equilibrium. On the other hand, if you add more ammonia to the system when it's at equilibrium, you now have too much ammonia. The system is no longer at equilibrium anymore. And so what will it do? It will break down some of that extra ammonia that you've added back into nitrogen and hydrogen. So we say that the equilibrium has to be shifted to the left. It needs to make more of the reactants until equilibrium is restored. So in summary, adding reactants to a system at equilibrium forms more products. It shifts the reactants to the right. Adding more products to a system at equilibrium causes more reactants to be formed. You are shifting the equilibrium to the left. So the same system. Let's say that instead of adding chemicals, we have a way of taking chemicals out. So if we are at equilibrium and now we remove ammonia without removing any nitrogen and hydrogen, we are no longer at equilibrium anymore. So if there's a deficiency, we need to make more ammonia. And so removing a product shifts the equilibrium to the right. Nitrogen and hydrogen have to react to make more ammonia to account for that was removed. And the opposite would happen had you removed a reactant. So removing products shifts the equilibrium to the right. Removing reactants shifts the equilibrium to the left. Let's look at an example here. So here's another reaction involving only gases. So we have ammonia reacting with fluorine to make nitrogen trifluoride and hydrogen gas. Let's assume the reaction has been going for some time and it is now at equilibrium. It no longer seems that the reaction is occurring, even though we know that the reaction is going to the right at the same rate it is going to the left. It is dynamic. So we want to ask ourselves, how will the equilibrium shift if we do any of these actions? First, suppose we add more ammonia to the container. Where's ammonia? Ammonia is on the reactant side. you have too much reactant now, and so it will shift the equilibrium to the right. Adding a reactant shifts the equilibrium to the right. What if you add hydrogen? Hydrogen is a product. Adding hydrogen means there's now too much of the products, so we need to break some of that hydrogen down, and so the reaction must go to the left. So adding a product shifts the equilibrium to the left. And finally, removing hydrogen from the container. Hydrogen is a product. If you, instead of add it, remove it, there's no longer enough hydrogen for there to be an equilibrium, so the ammonia and the fluorine will have to react to form more hydrogen, and so that will shift the equilibrium to the right. This is the end of the material for Chapter 5. Thank you.